In this artificial intelligence class, we will see the active reinforcement learning from third unit. And in today's class, we will discuss the adaptive dynamic programming, that is ADP agent, and then exploration by using 4 by 3 world. In this exploration, we will see the greedy agent and exploration equations. After that, the safe exploration by using some real-time examples. After that, we will see the temporal difference Q learning. Active reinforcement learning. When come to passive reinforcement learning, the policy is fixed and this policy determines the agent's behavior. But when come to active reinforcement learning, the agent have to learn the optimal policy, right? And the agent to learn the expected utility of each state and update its policy. So, this is active reinforcement learning, and this agent is a greedy agent, right. Here the active learning is an approach that gives higher weight to the unexplored actions and lower weight to actions with lower utilities, right. Let us see, this is the state S. On this state, the agent have to perform any of the action 1, action 2, action 3, action 4. So, the agent have to choose any of the actions to perform on this state. First it tries action 1, okay, and it receives the negative reward with -5 point, okay. Hence, the agent omits this particular action, then it will select the action 2 and it will get positive 1 point. Hence, it assumes that the positive 1 point action is suitable for this particular state, but this may be have +5 point, action 4 may be +5 point. That is what the active learning is, an approach that gives higher weight to unexplored actions, okay. So, action 4 is unexplored, hence the point is 5, and lower weight to actions with lower utilities. See, these two will get lower utilities. Now, the active learning agent gets to decide what action to take for the corresponding state or for the current state. Okay. Adaptive dynamic programming agent for active reinforcement learning. Okay, this agent needs to learn the complete transition model with outcome probabilities of all actions rather than just the model for fixed policies. Just now we have seen that it have to identify the suitable action for corresponding state and that is choose the suitable action, and the utility is defined by the optimal policy by Bellman equations. Here the utility function u of s, capital U of s, which is equal to max of a belongs to capital A of s summation of s dash p of s dash such that s comma a into r of s comma a comma s dash plus gamma u of s dash. Here a is nothing but action and capital A is nothing but all possible actions for this agent, and s is nothing but the current state. Okay. Now, the p of s dash such that s comma a means the probability of reaching state s dash. Okay. For example, we are in this particular state. From this state we need to reach the goal state here. Okay. What is the probability of reaching the goal state is defined here. Okay. This is what the probability. And next one is capital R of s comma a comma s dash, which is nothing but the reward of each transition. Okay. And gamma is nothing but the discount factor. Okay, the equation can be solved to obtain the utility function u using the value iteration or policy iteration algorithm. Okay. What is the goal of this agent? to maximize the utility. Maximize the utility for all the state is the main goal of the active reinforcement learning agent. Exploration. See, before this exploration, let us see one example, that is chess game. So in the chess game, the user should know the rules, isn't it? The user should know the rules, whether the user is playing well or not. They have to know the rules of chess game, that is the action of all characters in the chessboard. Okay. See, without knowing all those things, how the user will win the game to a very good opponent by multiple times. It is a very time consuming process, isn't it? So the exploration means in the unknown environment, the agent have to explore the unknown state to gain information to learn the policy and rewards. To learn the policy and reward by trying various actions on that state multiple times. Okay, this is called as exploration. And an optimal exploration scheme is nothing but to find the scheme that discovers optimal policy. The agent itself have to learn the policy, and it may take a longer time. Okay, and this exploration is also called as greedy in the limit of infinite exploration, which is simply called as GILI. Greedy agent. This agent greedily takes the actions and it believes to be optimal at each step. For example, see, this is the current state. In the current state, the agent will select any of the action to get S dash, and in the S dash it will perform another action to get S dash dash. That means this particular action will give some positive reward point, so that the agent believes that the action is optimal action for this state. Okay, likewise the agent believes what the action it select is correct. Okay, but sometimes this greed work out well and the agent converts the optimal policy, that is the agent finds out the optimal policy, but many times it does not work out, because some other actions may also have very great positive rewards, isn't it? So the greedy agent overlooked the fact that the action provide rewards. Okay, so based on the reward only the agent will select the actions. Okay, so the agent will get information from the actions, and the action also provide information about the form of perceived in the resulting state. Okay, see, for a particular action which resulting state we will get. Okay, so the action will provide reward points as well as the information about the neighboring state also. This diagram shows the one sequence of trials for the agent to find route from starting state to goal state. Okay, so the trial starts from this path. The path is like this is 1, 1. After that, this is 2, 1, again 1, 1. After that, 1, 2, 1, 3, 1, 4, again it will come back here. This is 1, 3, then 2, 3, 3, 3, then it will come back here, 2, 3, again 3, 3, then this is 3, 4, goal state. Okay, first in the first trial this finds this particular route to reach the goal state. Okay, and after the third trial it finds the policy, it finds a particular policy that reaches the reward, based on the reward along the lower route. Okay, it finds some another route, right, that is 2, 1, 3, 1, 3, 2 and 3, 3. Okay, so from this route it finds the goal state. Okay, hence it will fix some of the policy based on the reward. Okay, after experimenting with minor variations from the 8th trial onwards, it sticks to that policy. Okay, so in the third trial it identifies some policy and it will only this particular route. Okay, after once it finds a policy, then the agent will fine tune only that particular policy route and it never learn the other state. Okay, in other way also we are having one optimal route. Okay, if the agent moves in this way, here also we can find the optimal route, isn't it? But once the agent finds a particular policy, then it cannot come out to that policy. The greedy agent does not learn the true utilities or the true optimal policy. Okay, based on the reward, it stick to that particular policy and it cannot come out. Okay, the learned model of this greedy agent does not same as the true environment. Okay, the true environment and the learned model sometimes different, and what is the optimal in the learned model may be some suboptimal in the true environment. Okay, so the agent, as per our example, the agent learns this is the optimal route. Okay, but another optimal route is also there, this one, isn't it? So the agent does not go beyond this particular policy, so this will stick only this particular route. Exploration function. The active reinforcement agent use this exploration function to gain information about unknown states. What is the purpose of gaining information for this unknown state? To learn the policy, because there is no policy for active reinforcement learning, isn't it? So the agent itself tries to learn this policy by gaining the information about unknown state, and also gather rewards in future by adjusting exploration of current best action and maximize its short term rewards. Okay, for this example, the agent is having the following actions: move up, move down, move left, move right. Okay, see, for this particular state, which will give maximum reward? Okay, during short term, which action will give maximum reward? See, for that purpose the agent is using exploration function. Here the agent can move upside or it can move left side, isn't it? Both possibilities are there. It will select one of these two actions, which action will provide maximum reward. Okay, now the agent choose this random action. See, apart from all the four, it will select any one of the random action with the probability, which action will give highest probability. Otherwise it will follow some greedy policy. Okay, randomly it will select any of the action here. Okay, sometimes it is time consuming process. Hence what the agent will do, a better approach would give some weight to the actions which are rarely used. The actions which are rarely used, for example, move right may be rarely used, but sometimes it may give better uh, option or more reward for this agent. Okay, it may have plus 5 point and move up may give plus 2 point. Okay, so the rarely used action may give highest priority, and it assigns higher utility estimate to relatively unexplored state action pair. So by this way the agent use this exploration function for this mapping this state action pair. To identify the state action pair, it is important to update the ADP learning agent. ADP means adaptive dynamic programming, isn't it? And to rewrite the update equation to incorporate the optimistic estimate. Okay, the equation is u plus of s, which is equal to maximum of a f of summation of s dash p of s dash such that s comma a into r of s comma a comma s dash plus gamma u plus of s dash comma n of s comma a. Okay, here u plus of s is nothing but optimistic estimate of utility, and f is nothing but the exploration function, this f, and p of s dash such that s comma a means the probability of reaching the state s dash, that is the next state, and r of s comma a comma s dash means reward for each transition, and gamma is nothing but discount factor. Here n of s comma a, which is nothing but the number of times the action has been tried in state s. So this is n of s comma a. Here maximum of a, which is nothing but a particular action which gives maximum reward. The function f of un used to determine the high value of the utility u and the actions which are not been tried often, okay, that is which have less count n, that is some actions may tried very less number of time in a particular state, isn't it? We have taken only those actions. Here the function should increase the u value and decrease the n value. So with the minimum number of times the action will be tried on a state, we have to get maximum utility. Okay, f of un which is equal to r plus if n less than ne and u otherwise. Okay, here r is nothing but the optimistic estimate of the best possible reward, okay, obtained by any state, that is r plus, means the action which is tried n number of times in a particular state, that should be less than ne. Ne is nothing but a fixed parameter, okay, we randomly fix any number, for example 5 times. A particular action should try less than 5 numbers, then r plus, otherwise u is nothing but the utility. Okay, this function is used to make the agent try to each state action pair, okay, with at least ne times. That means all the actions should be tried in a particular state at least ne times. The safe exploration. For this we will see some example. First one is chess game. Suppose if we play the chess game with very good opponent and we lose the game, okay, no problem, we won't get any physical damage. From the game definitely we will learn something, very good information, and that make us better player in the next game, right? And second one, a self-driving car in simulation environment. Okay, the car is driving only on our computer, right? So we could explore the limits of car's performance, and if any accident happens, okay, no problem, the accidents will give more information, and because of that accident if our car crashes means no problem, immediately we have to set the reset button and we will get very new brand new car, isn't it? In the real world the scenario is different. Many actions are irreversible. For example, let us take this online search agent, it commits some mistakes, okay, and no sequence of actions can restore the state what it was before. That is, the actions cannot be reversible and we cannot get back to original state also. In some worst case, the agent enters absorbing state. That means no action can have any effect on that particular state and no rewards are received. The next one is an agent learning to drive a real car on the real road. Okay. Now the agent should avoid the following actions. The first one is the state with large negative rewards. Okay. For example, such as serious car crashes. Okay, we should avoid this. And second one, state from which there is no escape. No escape state we have to avoid. For example, driving the car into a deep ditch. Okay, there is no escape from here. And the third one is state that permanently limit the future rewards. That means damaging the car engine so that the maximum speed limit will get reduced. And that's all about today's class. In the next class we will see the temporal difference Q learning, and for more information please go through your textbook. Thank you.